students, welcome to another lecture in our course Environmental Modeling and Simulation. Today we will continue our discussion on 2D nonlinear system, and I will actually walk you through an example of how to qualitatively analyze a 2D nonlinear system. So let us get started. So in the last class we talked about how we decide the existence of a unique solution for a 2D nonlinear system, and the condition for that a unique solution exists in a given time interval around t equal to 0, which is from minus tau to plus tau, is that our function, our system should be continuously differentiable. So all partial derivatives of our function f with respect to all the variables should be continuously differentiable in the particular given domain, and only then we can say that a unique solution exists in this open connected domain, open connected set for this particular time interval. So there are a lot of conditions to this uniqueness and existence theorem. Now since we are only focusing on unique solutions, it also goes without saying that we cannot have non-unique solutions when we are using the approach for qualitative analyses. So if you look at a typical phase portrait, so let us say we have variable 1 here on x-axis and variable 2 on y-axis. Remember, we are dealing with non-linear 2D system. So we have two variables. In 1D system, what we did was we plotted the variable on x-axis and the velocity of the variable, the rate at which it is changing with time, on the y-axis, which is not the case here. In 2D systems, we plot the variables, not their velocity. So let us say this is our phase portrait for any system, and let us say the starting initial point is here in the second quadrant and our trajectory moves something like this. Now since at any given instance we cannot not have unique solutions, we need to have unique solutions to use this approach, what it is telling you is that the trajectories will never intersect. So let us try to intersect the trajectories and see. So here in this particular place, the trajectory is intersecting with itself. Or let us say, if this is not the case, so we have a phase portrait, another. So let us take variable a1 and a2, and we have one trajectory like so, and then we have another trajectory going like this. Now here also we have two trajectories intersecting each other. In this particular case, we have the trajectory intersecting with itself. Now the problem is at the site of intersection, so in this case it's here, and in this case we have two sites of intersection. What's happening in these sites of intersection is that the uniqueness theorem fails, because at the site of intersection the variable can go in multiple directions, more than one direction, so the solution loses its uniqueness. That is why when you draw the phase portrait, take special care that your trajectories do not intersect. Okay, now let's move on straight to our example. I'm going to take a very simple example of a 2D nonlinear system. It's from your textbook. So we have dx by dt and then dy by dt. So notice here this is an uncoupled system. Why I am saying that these two variables are not coupled with each other? Because the rate at which x is changing with time depends only on the current value of x. So basically dx by dt is only a function of x, and similarly dy by dt is only a function of y, not of x. So this is a very simple classic textbook example, and we are starting with a very simple example. Very soon when we run into Lotka-Volterra model for competition, predation and cooperation, we will not be dealing with such uncoupled or decoupled systems. In the last class, that the first step to solving a 2D nonlinear system is to find out the fixed points. Now even in case of 2D nonlinear systems, much like 1D system and 2D linear systems, fixed points are the points where there is no change with time. Once your phase point arrives at a fixed point, it stays at the fixed point forever, which means that dx by dt and dy by dt have to be simultaneously equal to 0. So remember, step 1, find the fixed points. So simultaneously we need dx by dt and dy by dt both to be equal to 0. Let's look at dx by dt is equal to x minus 1 plus x square. Let's make it equal to 0. We get 3 situations, 0, plus, minus 1. So, when x is either 0 or plus minus 1, dx by dt will be 0, x will not be changing with time. Now, let's look at dy by dt being equal to 0. The only situation when dy by dt will be equal to 0 is when y is equal to 0. So, now we have 3 different combinations. Our fixed points are I am writing x first and then y, 0, 0, plus 1, 0, minus 1, 0. Remember the format here is x, y. Okay, so we have found the fixed points. The next step that we have is to find the Jacobian matrix. So, the Jacobian matrix is basically the matrix of partial derivatives of each of your equations with one changing variable at a time. So, for this case, let's say I am calling this as a function f and this as a function g. So, Jacobian would be equal to del f del x, partial derivative of f with x, partial derivative of f with y, partial derivative of g with x, and partial derivative of g with y. So, I hope you can see the trend here. All the derivatives in the multidimensional system in the first column of this would be for the first variable xi, where I is equal to 1. Last column I will be equal to n. So, the last column will have derivatives of the functions, partial derivatives of the function with xn. Now, if you look at row, each row corresponds to a particular function. Okay. Remember this sequence, we have talked about it in the previous class as well. Okay, so let's go ahead and find the Jacobian for this system. I purposely chose a very simple example. So, this is going to be a very easy Jacobian. So, let's partially derive the first function with respect to x. Now, with respect to y, partial derivation will give us 0 because there is no y term in f. Now, let's look at g. Partial derivative of g with x will give us 0 because there is no x in g. With y, we will get minus 2. So, this is a very simple Jacobian that we get. Now, we will use this Jacobian to find our characteristic equation at each of the fixed points. So, this is our first step was to find the fixed point, second step was to find the Jacobian matrix, the third step is to find the characteristic equation, and we find the characteristic equation at each fixed point because we are interested in seeing how the trajectories are behaving around the fixed point, and then using that information we can qualitatively construct the whole phase portrait. Okay, so what is A at 0, 0, the first fixed point? What we need to do is substitute the value 0, 0 in the Jacobian. What do we get? Minus 1, 0, 0, minus 2. This is our characteristic equation. Right away, you can either choose to find eigenvalues and then eigenvector, or if you are slightly on the impatient side like I am, I want to find out tau and delta right away to understand how the system is behaving around the fixed point 0, 0. So, in this case, I see that tau is equal to minus 3. So, remember, tau is the trace of the matrix. Delta is the determinant of the matrix. So, determinant is 2. So, I am dealing with a situation where tau is negative and the delta is positive. Now, what is tau square minus 4 delta? I can easily calculate 9 minus 8 is equal to 1, bigger than 0 is positive, which means our point lies in the fourth quadrant and it is outside the curve. So, if you look at our diagram, the tau is negative and the delta is positive. So, we are in the fourth quadrant and we are dealing with a stable node. So, this is a stable node. Now, if you are interested, we can go ahead and find out eigenvalues and eigenvectors. So, let us go ahead and do that. So, remember we are dealing with A 0 0 and our characteristic equation was -1 and 2 in the trace. So, to find out the eigenvalue, we go the same old process, determinant of A minus I lambda is equal to 0. Students, it is a reminder from my end, please solve this on your own. Do not wait for me to solve it on the screen. The reason I am walking you through each step of this solution is in case you get lost or confused or you want to cross check your solution, you can always consult and compare it with mine. But please do it by hand, do it yourself, and that is how learning will be more fruitful for you. Alrighty, let's find out the eigenvalues. Since this is a stable node, I know that the eigenvalues are going to be negative because the movement will be towards the fixed point, not away from it. So, lambda is equal to -1, -2. Negative eigenvalues, it is a stable fixed point. Let's find the eigenvectors. So, for lambda 1 equal to -1 at this particular fixed point. So, to find the eigenvector, we need to substitute this value of lambda 1 into this and then multiply it by v1, v2, their product should be 0. Their product should be 0. So, what we will get here is -1 plus 1, -1 minus -1 will become +1, 0 minus 2 plus 1, v1, v2 is equal to 0. So, basically we get 0, 0, 0 minus 1 is equal to 0. So, for lambda 1 equal to -1, sorry I forgot this vector here, what we get is that v2 is equal to 0. This is our eigenvector. Now, v2 seems like not a very clear, maybe it is a little confusing, but I would be very happy to walk you through this. Remember, whenever we get a ratio of v1 and v2, what I like to do is take that number of steps. Let us say v1 by v2 is equal to 1 by 4. Take one step in the direction of x-axis and then 4 steps in direction of y-axis. Connect this and this is your eigenvector corresponding to particular lambda. Now, in this case, the eigenvector that we have gotten corresponding to eigenvalue -1 is v2 is equal to 0, which means no matter what my v1 is, whether it is 1, 2, 4, 10, my v2 is 0, which means corresponding to lambda 1 is equal to -1, my eigenvector is coincident with x-axis. So, I will write this down here, coincident with x-axis. Now, let us find out the eigenvector for the next eigenvalue, which is -2. Again, we are still talking about the first fixed point that we have taken up. Exactly the same process. What you will see here is that for corresponding to this eigenvalue, the eigenvector is v1 is equal to 0, which means no matter what your movement is in the direction of y, there is v1 is 0. This is coincident with y-axis, this eigenvector. Okay, now let us find out the eigenvalues and eigenvector and the behavior of our fixed point, the next fixed point, which is +1, 0. So, I am going to erase some things on this slide. So, for 1, 0, we are going to put, to find the characteristic equation at A, characteristic equation A at the fixed point 1, 0, we are going to put the value 1, 0 in our Jacobian. So, what we will get is put 1 for x and 0 for y, +2, 0, 0, -2. Very interesting scenario. Look what is happening here. The trace is 0 and the determinant is -4. Trace is 0, which means in our diagram here, we are on the x-axis and determinant is negative, which means it is not a center, it is a saddle point. Very important to find out the eigenvector and eigenvalue at this particular fixed point. So, this is a saddle node. See, I don't even need to find out tau square minus 4 delta for a saddle node because the curve does not exist in the second and third quadrant of our diagram. So, I hope this is a revision for you at this point. How do you find out eigenvalues and eigenvector when this is your characteristic equation? Very simple. Remember, A I minus eigenvalue determinant will be equal to 0. So, very quickly, so what we are getting is just a minor correction. Since we are talking about determinant, I don't need to put 0, 0 in a matrix form, it's just 0. So, we get lambda is equal to plus 2 and minus 2. Of course, this is a saddle, we have 2 lambda. They have same magnitude but different signs. Okay, now let's find out the eigenvectors corresponding to the given. So, we'll start with lambda is equal to plus 2. Lambda is equal to plus 2 and we are dealing with A10. Okay, another scenario where we will get V2 is equal to 0. When V2 is equal to 0, our eigenvector is coincident with, take a moment, pause this video and guess what it is coincident with. Alright students, I hope you are back and I hope you guessed it correct. When V2 is equal to 0, our eigenvector is coincident with x-axis. We just covered it in the previous example of the stable node. Now, what happens when lambda is equal to minus 2 and we are talking about fixed point 1, 0. So, in this case V1 becomes equal to 0, which means our eigenvector is coincident with y-axis. Now, what I would like to do is on a fresh slide, list down, summarize all the information that we are gathering here so that we can draw the phase portrait easily. So, I will take this slide. So, at the fixed point 0, 0, we have two eigenvalues, lambda 1 is equal to minus 1, lambda 2 is equal to minus 2. Here, the eigenvector is coincident with x-axis and here the eigenvector is coincident with y-axis. Then we have 1, 0, we have lambda 1 and lambda 2, plus 2, minus 2, and we see that in case of plus 2, the eigenvector is coincident with x-axis and here it is coincident with y-axis. Now, we have one more fixed point to go, which is minus 1, 0. So, I will do the calculation here and then erase it and then summarize and then we will draw the phase portrait. So, very important, remember your Jacobian matrix. So, now what we are going to do is look at the behavior of flow lines around the third fixed point, which is minus 1 and 0. So, I am going to do the calculations here and then I am going to write down the eigenvalues and the eigenvectors like we have done for the other fixed points 0, 0 and 1, 0. So, if we go back to our previous slides, we notice that this is our Jacobian for the system minus 1 plus 3x square, 0, 0 minus 2. So, let us write down that first. And let us confirm that this is correct. So, yes, minus 1 plus 3x square minus 2. Now, what we are going to do is we are going to put the values of the fixed point into this Jacobian. So, here we only have x, we do not have y. So, it is going to be a little easy. So, let us put minus 1 instead of x. So, what we will end up with is minus 1 plus 3 into 1, minus 1 square is 1, 0, 0 minus 2 and then this solves as 2, 0, 0 minus 2. Straight away what we can do is look at the tau and delta values at minus 1, 0. So, tau here would be the trace of this determinant and that trace is 0. And then the determinant is 2 into minus 2, which is minus 4. So, we have a negative determinant. So, we are already talking about the saddle node. So, if you look at our diagram here, when tau is 0, we are here on the x-axis, and the determinant is less than 0, which means we are definitely in the case of saddle point. If determinant was positive when tau is 0, we would be having a case of center, which is not the case here. So, what we can safely say is that minus 1 0 is also a saddle node. Now, remember one thing about saddle node, one of our eigenvalues would be positive and the other eigenvalue would be negative. So, the next step is to figure out the eigenvalues for our saddle node. Now, if you have a stable node or if you have an unstable node and you are not very interested in the shape of the flow lines, just knowing that they are stable node or unstable node is sufficient to understand the direction, the general direction in which the flow lines will move. However, with saddle node, since we have two eigenvectors both with opposing direction in which the flow lines move, it is very important to figure out the eigenvectors. And the first step in figuring out the eigenvector is to figure out the eigenvalues. So, let us go ahead and do that. So, as a revision, to figure out the eigenvalues, we use this matrix as a new characteristic equation. So, what we will have is, we will equate this to 0 and then we will find out our eigenvalues. So, let us do it. So, what we end up with is lambda is equal to 2 and minus 2, because here this is what our characteristic equation looks like, lambda is equal to plus 2 and minus 2. So, notice one thing, this is a very interesting case of saddle node where both eigenvalues are equal in magnitude but opposite in sign. So, now we can summarize this here. I do not want to erase much, so I am going to keep some of the rough work here. The fixed point minus 1 0, lambda 1 is equal to 2 and lambda 2 is equal to minus 2. If you look at it, this saddle node is very much similar to 1 0 saddle node. Now, what we need to figure out are the direction of eigenvectors to understand in which direction, in case of minus 1 0, do we have plus 2 eigenvalue and in which case we have minus 2 eigenvalue. So, to figure out the eigenvectors, what we need to do is, we need to take our characteristic equation, we need to subtract identity matrix multiplied to corresponding eigenvalue, and then we need to multiply it with the matrix that has only the eigenvectors and their product should be 0. So, it will look something like this. And let us take the first case where lambda is equal to plus 2. So, when lambda is equal to plus 2, this particular matrix will reduce to okay. So, this is a very fascinating case. What we have here is the product should be 0. So, now what we will have is 0 V1 plus 0 V2 is equal to 0 and we have 0 V1 minus 4 V2 is equal to 0. Clearly, the first one is a non-solution and this one too is not very helpful. What we end up is that V2 is equal to 0. So, notice V1 is the movement in x direction, V2 is in y direction. V2 is 0 means this is coincident with x axis. Now, let us figure out in the other case when lambda is equal to minus 2. So, when lambda is equal to minus 2, this particular equation will resemble this. So, what we end up with is that V1 is equal to 0. When V1 is equal to 0, it means that this is coincident with y axis. So, if we go back to our slide here, we can say that this lambda 1 is equal to 2 is coincident with x axis and lambda 2 is equal to minus 2 is coincident with y axis. So, you see that quite literally 1 0 and minus 1 are mirror images of each other. Both have saddle node, both have exactly the same eigenvalues and corresponding eigenvectors. Now, we are going to draw the phase portrait. So, the first step in drawing the phase portrait is to draw the axes. So, I am going to use a different color for drawing the phase portrait. So we have x on x-axis, y on y-axis. Let's plot the fixed points first. So the first fixed point, let's say, is 0, 0. And then we have 1, 0. And we have minus 1, 0. So 0, 0 is a stable node, which means it's attracting. And we even know in what direction it is attracting. In x-axis, the eigenvalue is minus 1. In y-axis, the eigenvalue is minus 2, which means the rate at which the point will move in the y-axis direction will be faster than the rate at which it will move in line with x-axis. So the attraction of the flow lines is happening in both axes. The corresponding lambda value for x-axis is minus 1 and for y-axis is minus 2. This is very important information because remember, the flow lines are tangential to the slower eigenvector. The slower eigenvector in this case is the x-axis. So we know that whatever lines do come here, flow lines will be tangential. So let's use another color for flow lines. The flow lines will be tangential to the x-axis. As a reminder, the reason why flow lines are tangential to the slower eigenvector is because the trajectory moves much faster in the direction of the faster eigenvector. We have discussed this at length in previous lectures. So if you want to revisit this, revisit the other lectures. Now let's draw at minus 1, 0. For minus 1, 0, x-axis corresponds to the unstable eigenvector and y-axis corresponds to the stable eigenvector. So x-axis unstable and y-axis stable eigenvector. So unstable means it's moving away and stable means it is moving towards the fixed point. So our flow lines are like this, which you see are in complete harmony with the flow lines around 0, 0. Now let's draw our flow lines around 1, 0. So if you look at 1, 0, quite similar behavior. The unstable axis is the x-axis eigenvector, and the eigenvector which is coincident with y-axis is the stable one. How do I know unstable and stable eigenvectors? It's by looking at the value of eigenvalue. If eigenvalue is positive, then the growth in that direction would be exponentially away from the fixed point. If it is negative, then there would be an exponential decay towards the fixed point. So we see a very similar behavior, unstable direction of x-axis, stable in the direction of y-axis. So this ends up being our phase portrait. Alrighty, so we know how the flow is around these three fixed points. Now we need to put this information together and draw a tentative phase portrait. So x on x-axis, y on y-axis, we have three fixed points. So when we put them together, let's draw the eigenvectors first, because we know how the flow is in these directions. Okay, so we know how the flow is in this direction, and then now we can fill in. Now any initial point that is close, and this is 1, 0, 0, 0, minus 1, 0. Let's say a fixed point is here, it is governed by the saddle node here, and as it comes closer to the x-axis, it starts moving towards this fixed point, which is an attractor. So eventually, tangential to the x-axis, remember, tangential to the slower eigenvector, it will end up like this. Similarly here, we'll get and here we'll get like so. There is a difference on left hand side and right hand side of this particular fixed point. On right hand side, these trajectories will meet the x-axis at x equal to infinity. On left hand side, at x equal to 0, y equal to 0, these trajectories will meet the fixed point. We'll see a similar behavior here. So my dear students, this is our phase portrait. Now notice that I have not filled this phase portrait with trajectories. I have drawn indicative trajectories to help you understand the direction of motion. When you draw the trajectories, make sure that the trajectories do not intersect, they are smooth. And yeah, that's pretty much it. All right, students, thanks for joining us for this lecture. In the next lecture, we'll explore the much awaited, the very versatile and very important Lotka-Volterra model of competition. Thank you.